Assalamualaikum and greetings to Doctor and my friends. So today I want to give you an explanation about our question, which is from Module 5, which is question number 1, F and G. So first of all, I want to introduce my group mate, which is the first one is our leader, Nurul Shazwani, and the second one is Liridi, and the third one is Hadiri, and lastly myself, which is Muhammad Ilham bin Sudirman. Hi everyone, in this video, I'm going to explain the solution for question 1F, which asks us to find the number of units of input L or labor that maximizes the average product of labor, which is APL. So, before we start, let's recap our APL function from our previous calculation in part C. After substituting the fixed capital K equal to 10 into the main equation and dividing it by L, we obtain the average product function, which is APL equal to 450L minus 100L squared. Now, our main goal here is to find the exact value of L that make this function reach its highest point or its maximum value. To maximize any function in economics, we need to apply differentiation. We take the first derivative of APL, with respect to L, and then we set it to 0. Let's differentiate 450L minus 100L squared. Derivative of 450L is 450. The derivative of negative 100L squared is negative 200L. So we get D bracket APL bracket divide DL equal to 450 minus 200L. Next, we set this equal to 0 to find the critical point. 450, we deduct with 200L, we get 0. Now, let's solve for L. We move the 200L to the other side. 200L equal to 450, and we put the L in front, and we get L equal to 450 divided by 200, and that gives us the value of L, which is 2.25 units. Well, it means that the firm will achieve its highest labor productivity, meaning the maximum average output produced per worker when exactly 2.25 units of labor are employed. If the firm hires more than 2.25 units of labor, the average production per worker will actually start to decline because of the law of diminishing returns. Therefore, L equal to 2.25 is the peak efficiency point for our labor input. That is the complete answer for 1F. Now, let's move on to question 1G and look at the boundaries for the three levels of production. I will start by explaining stage 1 because the next stage will be explained by my group mates. Stage 1 is the initial phase of production. The boundary for stage 1 starts from L equal to 0 up to L equal to 2.25 units of labor. If you remember, 2.25 is the exact point where our average product APL reaches its maximum, which we just calculate in part 1F. So, what is actually happening in this stage? At this point, the firm has plenty of machines, which is 10 units of fixed capital, but very few workers. Because there are so many machines available, every time the firm hires a new worker, the workers can specialize and use the machines more efficiently. As a result, both the marginal product MPL and the average product APL are increasing. In fact, throughout stage 1, the marginal product is always greater than average product MPL. In economic terms, is considered an efficient stage to stop production. Why? Because the firms underutilized machines mean that adding more labor will continuously drive up the average productivity of the workers. Therefore, a rational business owner will never stop hiring in stage 1. They will keep pushing through until they cross the boundary of L equal to 2.25, which marks at the end of stage 1 and at the beginning of stage 2.
Okay, now I will continue to for the stage 2, where the boundaries range from L equal to 2.25 to L equal to 3.0 unit, beginning exactly from the maximum point of APL and continuing up to the point where the total product reached its maximum level, which is where the marginal product equal to zero. This specific stage is highly critical for any firm as it represents the most rational and economic zone of operation where inputs are utilized efficiently. Next, moving to the stage 3, where the boundaries begin with the input at exceed 3.0 unit. A firm will completely avoid operating in stage 3 because this is the phase where the total product start to decline, causing this marginal product to drop below zero and become negative, meaning that adding more unit of input L will only decreasing the total output. Okay, now moving on to this slide where we have the step-by-step mathematical working to show how our boundaries were derived. First, looking at the left panel where we given that input K is fixed at 10 units by substituting K equal to 10 into the original production function. Uh, we get function Q equals to 4.5K square L square minus 0.1K cube L cube. We get the Q equals to 4.510 uh, square L square minus 0.110 cube L cube, and simplifying the calculation give us our final total product function, which is x equal to 450 L square minus 100 L cube 100 L cube. And next we move on to the middle panel, which is how show how we find the function and maximum point for the average product of labor APL. To determine the stage 1 boundary, we find the APL function by dividing Q by L, which give us APL equal to 4050 L minus 1000 L square. To maximize this APL function, we take its first derivative with respect to L, which give us d bracket APL or DL equals to 4050 minus 200 L, and we set it equal to 0. Solving the linear equation, 200 L equal to 4050 give us L equal to 4050 or 2000, divided 2000, resulting in as a value of L equal to 2.25 unit. And next for the last panel, which is the right panel, show us how we found the boundary for the stage 2 by determining where the marginal product of labor MPL equal to 0. The MPL function is delivered by taking the derivative of Q with respect to L, which gives us MPL equal to dQ or dL. dQ divided or dL equal to 9000 L minus 3000 L square. To find the maximum capacity where the MPL equal to 0, we set 9000 L minus 3000 L square equal to 0 and factor out the common terms to get 3000 L bracket 3 minus L equal to 0. This gives us two roots where the 3000 L equal to 0 lead to L equal to 0 for the start of stage for the start of the stage 1, and 3 minus L equal to 0 lead to L equal to 3.0 unit, which mark the end of the stage 2 and the boundary for the of the stage 3.